This year, we are celebrating the 60th anniversary of one of the greatest inventions of the 20th century, that is the laser. It was in 1960 that the American physicist Theodore Myman invented the laser. Since that time, the laser has crept into a huge number of applications in everyday life. And I'll be talking about the development of the laser during the next few minutes. Now, before we move on to the laser, I have burning here three, what I hope you find are very, very beautiful flames. And the reason is that since the earliest of times, people have always been fascinated by flames and by fire, and especially the colours which they produce. And these are the flames which were known, these colours were known in ancient Chinese fireworks. And the reason why is the Chinese had learned to make fireworks over 1,000 years ago, and they knew that by adding certain substances, they could achieve colours such as this. Now, to the naked eye, these colours seem to be red, orange, and a sort of a bluey green, traffic light colours, you might say. But what I'll be explaining to you during the course of this talk is actually each of these colours is made up of a large number of quite independent colours, which obviously are very similar. So we'll come on to that later on, but in the meantime, I'm now going to take away our fires, our beautiful burning flames, and put them out, and then we'll start talking about lasers and how they are quite different from the flames that you are seeing. How the light which a laser gives off is quite different from what we're seeing here. I'm just going to pour water onto here, and as I pour water, you will see that the flames gradually will disappear. So there we are, just pouring on the last one here like this, and we can just let that gently sit in there until the end of the talk. So, if I'm talking about lasers, first of all, I suspect I should tell you exactly what a laser is. Well, it's a device for producing a special type of light, an intensely concentrated beam of light, which is coherent. The word there is coherent. Now, what does coherent mean? It means essentially two things. The light, all of the light that comes out has exactly the same wavelength, and I'll be talking about that later on. Furthermore, it is coherent, which means that all the waves move up and down together in the same phase. And that is it. And they're very, very concentrated. And this type of light has a huge number of applications in today's world. As I'm sure you know, whether it's scanning your barcodes on items which you purchase, it's used in surgery, in the medical world, in microsurgery, it's used for welding, it's used in extremely refined equipment in the fire industry, fire engineering industry, for detecting tiniest amounts of smoke. It's used on a huge scale in fibre optics, in communication, and in laser printing, just to mention a few of the uses of lasers. So what is a laser? It's an actual device for producing this. And I shall now just show you, I've drawn a diagram for showing this, and I'll explain how very briefly this works. So the word itself, laser, stands for light amplification by stimulated emission of radiation. Light amplification by stimulated emission of radiation. And this is a typical diagram which I've just drawn just to show the major components. It's very, very crude indeed, but we could just go through. So in blue we have the outline, which is the sealed container with a light producing substance which is known as the gain medium. Now the gain medium can be a solid a liquid or a gas, and solids are semiconductors, diodes, and for instance also glasses, crystals, etc. Gases are, for instance, a mixture of helium and neon or carbon dioxide, and liquids are dye-stuffs dissolved in various solvents. That's just a few examples. Number two is the power supply drawn here in green, essentially a source of direct current electricity which can produce a variety of heating and lighting effects. Number three is this, what we call the optical cavity or the resonator, which concentrates light to stimulate emission of laser radiation, and that laser radiation is produced coming out here as a controlled beam of laser light, and the way this stimulation also occurs, it's by the light moving backwards and forwards between two mirrors, which I've got two mirrors, one of which is fully reflective and the other is partially reflective. And that movement of the photons, because that's what these light particles of light are called, they're almost, we can describe them as tiny packets of light, photons, they go backwards and forwards, and they induce a sort of a chain reaction, of a cascade of these particles, light photons, which come streaming out in the form of a laser beam, which is so useful. So that is it in essence. I've explained in a very, very simple manner the components of a laser device itself. And I have also said what a laser beam is. Now, that definition, I'm sure you recognize, is quite complicated. And in order to understand it, I'm going to go through a little bit through the history of light and our understanding of light. Now, one of the crucial experiments which occurs was this wonderful experiment which I have to show you here with a prism. Isaac Newton in 1666, Isaac Newton demonstrated the fact that a rainbow is made of 7 colors, or white light from the sun is made of 7 colors. We know that rainbows were, of course, that's obvious, but how did they come about? It was by the splitting of the white light by the process of refraction. And the water droplets in a rainbow acted as a giant refractor. But here you see I have a small projector, and there is a beam of white light which comes out through the slit which has been made there. But what I'm going to do now is insert a prism there. And as I insert a prism, you'll notice the development of a beautiful miniature rainbow there. Now that miniature rainbow there is, as you know, the decomposition of the white light which is coming out from our bulb there, and it is splitting into the various colors of the rainbow by the process of refraction. So there we are. This is Newton's experiment, first conducted in 1661, 1666 should I say, which is the year of the Great Fire of London, by an extraordinary coincidence. Now, Newton furthermore formulated, he was very curious to know how light is, how it operates, what's it made of, is it a particulate substance, is it a wave pattern, or is it a substance indeed? And he formulated what we call the corpuscular theory, that light is made up of particles which travel through the ether. That was his idea. It explained some of the phenomena of light, of reflection, but not everything, but not every phenomenon. And so people were still asking the questions, what indeed is light in more detail? And here I just wanted to show you, I'm going to move on to another very, very important experiment in the history. These glasses here contain diffraction gratings. They're thousands of lines ruled, and please watch carefully. We have our slit there, and if I put this in front, then you'll notice that next to this slit, once again, we can see the rainbow, but it's not moved further away, and this is the process of diffraction. Now that process of diffraction is, I'm going to show you, was invented or was first investigated by the physicist Thomas Young at the beginning of the 19th century, around 1802. And in this very crucial experiment, Thomas Young supported the other theory, was able to give evidence to the other theory which had been put forward, and that had been put forward in 1678 by the Dutch astronomer, mathematician, natural philosopher Christian Huygens. And Huygens had said that in his opinion, light is actually made up of waves which are propagated down through the medium. And I can just show you a very, very simple and basic experiment of a wave. Here I just have a piece of black cord, and it's tied to a weight. And if I just I just give it a flick, you can see a wave going down. So that really is very, very simple. But these two ideas which I've just talked about, the idea that light is made of particles or that light is made of waves, have been absolutely predominant in the way that we have understood through our experiments the nature of matter and the nature of energy. These are two topics which I will be taking side by side and explaining how they are related, especially with reference to light. But before I go forward any further, I just wanted to show you three devices which I have here, three devices for producing light, to illustrate the differences in the different kind of lights that we use on an everyday basis. Here you see I have a laser, and there it is, it's a red laser. This is, by the way, 120 milliwatts, so it's quite a powerful laser, taken from a DVD, I suspect, or some sort of device like that. Here I have now a different type of light, and that is produced from a torch, and that's white light there. And then I've got another type of a torch here, which I'm going to show you on the wall there. Now you see these three types of light which we use on an everyday basis are quite different in nature. The one at the top is produced, it's a warm light, as you can see, a warm white light, and it's produced by a filament which is heated to a very high temperature, and it gives off a type of a radiation which consists of many, many different wavelengths. It's quite similar to the sort of light we get from the sun, but it's highly dispersed, it's incoherent and dispersed, and also quite a lot of heat energy is produced. So this is not very efficient, but nevertheless, it gives off quite a nice light, which is very useful. Now, the one in the middle, of course, is the laser. And as I said, this is the narrow beam of coherent light of very great intensity. And the one below, which I've shown you, is the one which is very popularly used today. And that is a white light, which is produced by light-emitting diodes, LEDs as they're popularly called. And in this torch, there will be three such LEDs. There will be a red, a blue, and a green. And when combined together, they will give white light. Now, the spectrum of an LED is quite close together. So in other words, it's not a fully coherent, it's certainly not coherent, it's not monochromatic, but the colours of the various individual LEDs which exist do give quite a sharp, narrow range of wavelengths of light. But as the white light is obviously produced by three different colours which have been built into this torch. So there we are, just a short demonstration then of three types of light and a little bit of information about how they are produced. But now let us continue. And as I said, throughout the talk, I will be focusing on two aspects of our studies of experimental investigations, the study of matter and the study of energy. And the latter, both of these are very difficult, but the study of energy is particularly difficult because energy is intangible. You can't actually touch some heat. You can't touch some light or electricity. They're invisible. We recognize energy by its capacity to do work, which is the formal definition of energy. Energy is the capacity for doing work. And just to give you an idea of how very, very difficult this topic is, the great French chemist Antoine Laurent Lavoisier included in his table of elements such as carbon, hydrogen, sulfur, he included also light and caloric. Caloric is of course, the French for heat. But these are two forms of energy. Now that doesn't show you that he was stupid. It just shows you how very, very difficult these ideas were. So I will try and give a little bit of insight into how our understanding of these has developed over the past 2 centuries. Now, a great advance in, so I've said Young was the person who was able to analyze light by using a diffraction grater. He actually had 2 slits. He obtained fringes, or it's like when you throw 2 stones into water and then they create 2 sets of ripples. And when the ripples overlap with one another, you can either get constructive interference or destructive interference, as we call it. And so you get this interesting patterns. And that's what happens with light, because light is made of waves, and his experiment proved it. Not only that, Thomas Young was actually able, using his slits, to measure the wavelength of light. So that was quite extraordinary. The wavelength of light is very, very small indeed, as you can imagine. It's approximately in the range of 500 nanometers. Now, that is the way I've calculated to make sense to me. It's approximately 1/2 of a thousandth of a millimeter. Now, just in case you're wondering, can you attach any reality to that? I've done some checking out. It's approximately in the same order of range as a piece of gold leaf, as the thickness of a piece of gold leaf. That's the sort of range that we're talking when we're talking about the wavelength of light. So this was a great step forward. So by the time Young had calculated the wavelength of light, the idea that it was a wave pattern had been firmly established and understood. And then on the topic of matter then, or the study of what things are made of, another great step forward was made in 1808 with John Dalton's atomic theory. Now, the idea of chemical elements as being substances which can't be broken down into simpler substances had already been well established over 100 years ago. But John Dalton came up with the idea that every element is made up of tiny particles called atoms. And for instance, I can just show you this, a silly little demo. Look, this is, let's say, an atom of hydrogen, and this is an atom of sulfur, say, for example. And in Dalton's theory, every single element, and there were probably about 30 or 40 elements known at that time, they all had different atoms, so the spheres would have had different sizes, they may have had different colors, and atoms were indestructible, and they combined together to form compounds, but they didn't change when they formed these compounds. So those were some of the ideas of Dalton's atomic theory. The main idea, though, that's relevant to today's talk is the fact that atoms are indestructible. They're indestructible spheres, and every element has atoms which are unique to that element, and that's the way things went forward from there. And this was a huge success in our understanding of matter, made of particles called atoms, which are present in elements. And now let's go back to our looking at light. You see, when Newton did his experiment with the spectrum, this was a terrific success, and as I said, his particulate theory became his corpuscular theory. Although it didn't meet with immediate success or recognition, was superseded, nevertheless it prompted a further investigation of the sun's spectrum. Now, a remarkable discovery was made by the German physicist Joseph Fraunhofer, because he found out on a close analysis, remember lens technology, the instruments were improving all the time, a close analysis of the sun's spectrum revealed a remarkable number of black lines. So instead of just having red, orange, yellow, green, blue, indigo, violet, those colors were there, but in the high magnification, there were several lines. And I just wanted to show you. I have here a book which is called The Story of the Sun by Sir Robert Ball, published in 1901. And I can show you inside a beautiful diagram here of the solar spectrum as it was seen by Joseph Fraunhofer. And as you see, there are lots of black lines. Now, Fraunhofer counted no less than 547 of these black lines, and this too caused a great deal of interest in the world of science, because people said, well, that's absolutely amazing. Where did these black lines come from? What do they represent? No one knew. It remained as a mystery. So that's another interesting step forward in our understanding of light as a form of energy, or indeed, is it still energy? People were still debating whether it was perhaps made of something, some matter. And then that was another big step forward, as I said. And then people continued to investigate other properties of light. So the Faraday, these lines were present was one issue, but the great chemist, the physicist, Michael Faraday, one of the greatest experimenters of all time, also had done a huge number of experiments in electricity and magnetism. And he was the person who invented electric motors, dynamos, and also did a huge number of experiments on electrolysis. He investigated the effect of an electric current on liquids. Now, I'll come back to that first of all, but Faraday, when he'd done his work on magnets and on electricity, became convinced that light had some sort of magnetic properties. Faraday investigated the magnetism of just about anything he could lay his hands on. Light was difficult to capture, but nevertheless people were beginning to do experiments with it. So Faraday did experiments to try and prove that light is magnetic. And he started his experiments in 1822 and got absolutely nowhere with them. However, he kept on plugging away. Like many scientists, they plug away until they get a result. And by 1845, Faraday had indeed achieved a remarkable result. Using the apparatus which I'm going to show you here, this, by the way, this elementary treatise on physics. Now, Atkinson was actually the translator. The author was Ganot, who was a Frenchman. This was published in 1910. And this shows you an apparatus which Faraday used to actually bend light waves using a magnet. There are two ginormous electromagnets there. There is a candle burning at one end, and there is a measuring device and a crystal in the middle, because it was actually plain polarized light, but it doesn't matter. He got the effect which he wanted to achieve. He proved experimentally that light actually has a magnetic property, is magnetic. Now, at that stage, in the world of physics and the world of chemistry, that did not have any great significance. And it wasn't until 1865 that the great Scottish physicist James Clerk Maxwell actually formulated the electromagnetic theory of light and put mathematics to it, and then put this on a very, very sound level, our understanding of the electromagnetic nature of light, and indeed the whole concept of an electromagnetic spectrum way beyond visible light. So that was Faraday, you see, then investigating the electromagnetic effects on light. Now, in the meantime, people had started to develop more apparatus for investigating light and the way these various lines are produced or indeed absorbed, as I'll explain very shortly, in various pure substances. And the flames which I showed you at the beginning, there were the flames which were produced by an alcoholic solution of copper chloride, lithium chloride, and sodium chloride. The three metals are the important points: copper, which was the blue-green one, lithium, which was the red one, and sodium, the orange one. Now, as I said earlier, those appeared to be one color only, but two physicists, Robert Bunsen and Gustav Kirchhoff, in 1845 developed a highly sensitive piece of equipment to study the light which is given off by using the process of refraction, by prism, by splitting it up and magnifying it and examining it very closely. And they could then detect, not only could they detect the various lines which were produced, but they could also measure their lengths. And here I have, again, with our physics textbook from 1910, I have here a diagram of the spectroscope, which was developed by Bunsen and Kirchhoff, and we're looking at approximately 1860 now. So using this apparatus, which consists essentially of 3 tubes, one of them is a telescope, one is a collimator, and another one is a reading tube with a magnifying glass with a scale on it, and in the middle there's a prism, and there's also a light source in the form of a candle at one end. But this, you see, this type of apparatus was the beginning of a new type of scientific apparatus, the spectroscopes, and that which was based using optical techniques, so lenses, and this was a further development from microscopes, telescopes, and now we had spectroscopes, and we were beginning to look more and more inside ultimately what matter is made of. So when they developed these spectroscope, when they developed the spectroscope in 1860 approximately, they then started looking at the flame colors of various elements, including, of course, copper, sodium, and lithium. And they made the remarkable discovery that every flame is made up of an element, is made up of a series of lines, which was called a line spectrum. And I can show you, I have here, this is a chemistry textbook from the 1977, it's from the Nuffield A-level chemistry course, and there you see beautiful, these are emission spectra of a number of elements, literally just to show you that they all have different lines. And you see hydrogen, sodium, potassium, calcium, strontium, and barium. These are just a few of the metal elements. But what is interesting to tell you is that not only do these elements, but every single element known to man is able to produce such a spectrum. And so Bunsen and Kirchhoff recognized the fact that a spectrum, if you can get a spectrum by irradiating a substance, then you would be able to, by heating it up to a high temperature in a flame, or by passing a high electric potential through it, then you could get a certain type of radiation which can be analyzed. And what these spectroscopes did, they analyzed it. And Bunsen and Kirchhoff recognized the fact that a fundamental property of every element is its spectrum. And to that effect, a new technique developed called spectral analysis. People were able to analyze the spectrum and to show the presence of elements in various minerals, etc. And I have a book here published in 1952 just to show. This is called Practical Spectroscopy, and it contains details of all the spectral lines for every single element. Just we can open it up there on the page for oxygen. It gives a little bit of the history of the discovery of oxygen, and then it tells you the important spectral lines, etc. And so, although these spectral lines were now being used for analytical purposes, although they were being able to serve a very useful purpose for analyzing elements, no one knew how they were produced. And indeed, what I've shown you in this diagram were spectral lines which were produced by the emission process, in other words, giving off, like I showed you at the beginning. But the black lines, which had been seen by Fraunhofer, they were exactly the same lengths, they had the same frequency, but their wavelengths, but these lines were black. And they were part of what we call an absorption spectrum. So can you say, does that mean that we could actually find elements on Earth that were present in the sun's corona or on the sun? The answer is yes. And indeed, elements on the sun's surface, especially when they give out their radiation, the radiation is absorbed in the sun's corona, and therefore we only see what's left over. And that's why we've had those black lines. And I'm sure you know that the element helium, for instance, was discovered on the sun. The word helium is derived from the Greek helios, meaning sun. And the reason why it was discovered on the sun, because its spectral lines, which it showed were quite unique. Incidentally, they've now found 15,000, 20,000 lines on the sun. So our capacity for seeing all these details and measuring quite extraordinary. And now we carry on to Crookes. Now, what was happening? In the meantime, at one stage, people were investigating these spectral lines and light and the behavior of light. At another end, though, they were investigating the properties of matter and the way it related to light. Now, essentially, the story goes back to the discovery of electricity, of current electricity, by the Italian Alessandro Volta in 1800. Volta had first created batteries by using dissimilar metals, and he tested the electric potential on his own body. So he used to apply the electrodes, his eyes used to see sparks, he used to get thunder and lightning going on in his head. He applied huge currents to his body, and he recognized that this was a very powerful and potent source of energy. Now, in a very short space of time, within 10 years, scientists had recognized the enormous potential of this new type of energy, electric energy, and they started carrying out numerous experiments to see what happens when you start applying an electric potential across a variety of different substances. And there were three types of substance: solid, liquid, and gas. Now, with solids, they would either conduct or not conduct. So metals were conductors. There were a huge number of solids compounds which were non-conductors. And that was essentially it. And they investigated, obviously, the effects on metals, and they found then that you could induce a magnetic effect. That was Ørsted 1822. They found out that the wire would heat up as well, the thermoelectric effect, and so forth. But when they started investigating liquids, a remarkable discovery is made. And the discovery that was made was that certain liquids, which we now call electrolytes, were able to be changed by a passage of an electric current in a reaction which we call electrolysis. And this started raising very serious questions about Dalton's atomic theory and the idea of atoms as being entities which cannot be changed in any way. Why was this? Because, say for instance, Humphrey Davy, the great chemist, had electrolyzed molten sodium chloride. Sodium chloride is common salt. We use it every day on our tables with our food to make them salty. Now, that is white crystalline solid, but when you split it into its elements by the process of electrolysis, there is a remarkable change. The sodium comes out as a metallic, a soft silvery metal. The chlorine comes off as a green gas. And people could not understand how is it possible for these atoms, which are spheres and which never change in accordance with Dalton's theory, how is it possible that these atoms can undergo, what happens to them during this process of electrolysis? Clearly, the electricity is having some very significant effect, but no one could quite understand it. Now, this issue of electricity and ions, electrically charged particles, was continuing to evolve in liquids, was continuing to evolve throughout the 19th century, right up to the end of the 19th century, our understanding of charged particles in liquids. But on the subject of gases, it was much more difficult still, because the only observation of a gas conducting electricity had been lightning, of course. Lightning strikes, which have been known since time immemorial, they represent the concept or the phenomenon of electricity being conducted through a gas, because air, of course, is a mixture of gases, and so the lightning strike there. But when they tried to do experiments in laboratories with conduction of gases, no one got anywhere for many decades. However, with the development of glass blowing technology, with the development of instruments for making, or apparatus for creating, a high vacuum, progress started to be made. And then the interesting effect, and I'm just going to go, William Crookes was a physicist, and he became famous for his cathode ray experiments. What this meant was he was able to take a long glass tube, he was able to evacuate it, put some gas in it at a very, very low pressure, and he had electrodes with a very, very high potential applied. And when he applied the electrode, the high potential across the electrodes, a remarkable effect occurred. They started giving off various glows. A light started to be produced. So this was a remarkable conversion of electric energy into light energy. Where does this light come from? That was the big question. And I've just got a textbook to show you here, a textbook, a second course of electricity by Mackenzie, published in 1959. And here you see, these are the sort of results that William Crookes achieved with the same gas, with the same voltages applied, but with gases at very, very low pressures. And there you see different effects. You have streamers, you have a pink discharge, you have striations, you have various effects, which were actually quite remarkable. And Crookes was very, very, very curious to know. In fact, the whole world of academia was very keen to know what on earth what is it that's causing all of these effects, you see. So Crookes came up with the idea. He did a variety of experiments because he was interested to know, is light actually, are these cathode rays, as he called them, are they material or not material? Is it energy or is it tiny particles? We're back to our debate of Newton and Huygens. But you see, and he was particularly renowned for this very beautiful experiment. He did what's known as the paddle wheel experiment. And I just wanted to demonstrate this effect to you, which has now been translated into a sort of a popular scientific curiosity, which is called Crookes radiometer. Now, at that time, they were also investigating the effect of radiation on bodies, black bodies, etc., and the interconversion of different types of energy. Now, Crookes did this. What I have here is a little weather vane, and if I point some violet light from my laser, little small laser, let's see, at the moment you see nothing is happening, but this will shortly, we'll just change it around to another direction here. Let's see, it takes a little, sometimes it, there we are, I think we'll get it going. I think we probably need to just turn it, there we are, I think we're getting going. I suspect there's a little bit of a spot there that we call a tight spot. There we are, we're getting going. And as you see, I'm shining my laser onto the black surface. There are black surfaces on one side of the vane, and they're made of mica, of very thin material, and there are white surfaces on the back. Now, what I'm shining on this is pure electromagnetic radiation. I'll explain that in just a second, but I'm shining light energy. Now, this was the problem, you see, this was the issue rather. Crookes believed that this was a demonstration that light is actually made up of particles, which you couldn't see as they flowed, but the effect was quite clear. He said there must be particles flowing. And this became, it was known as the paddle wheel experiment, which we have here in a different variety. And what I wanted also to tell you, that inside this glass bulb is a gas at a very, very low pressure. I don't know how low, but it's almost a complete vacuum. But the way that this works, Crookes thought that this was caused by the particles knocking against the black surface. But in fact, we now know that it's caused by the fact that the black surface absorbs the frequencies of the radiation and converts them into heat energy, because black surfaces absorb heat very effectively. And as they become warm on one side, so this causes the molecules on that side to vibrate with more energy and exert a greater pressure than the molecules on the other side, and that's why the wheel starts to turn. So this is a remarkable demonstration of the interchange of three types of energy: electromagnetic radiation from our laser, the heat energy, which is produced as it strikes the black surface, and mechanical energy, which is the turning of the wheel. Now, Crookes was, as I said, investigated these cathode rays, but it was, and he said that they were negative, but the man who actually finally proved that they had negative charge was the French physicist Jean Perrin. So, and that was quite a few years after Crookes had done his experiments. I think we're looking at 1895. Now, the next big step forward came with J.J. Thompson's extraordinary experiments, once again with the negative particles or electrons. Now, what Thompson did, and this was the great breakthrough, Thompson actually was able to prove experimentally that the particles which are responsible for these negative rays are actually particles which are called electrons. So he actually was able to state for the first time that the electrons are present as tiny bits of negative charge inside every kind of atom. Now, this was a major contrast to it was a step forward from Dalton's view of atoms. Dalton said that atoms were totally indestructible. We now have the idea that actually every atom is made up of two types of particle. Well, it was one initially, it was just one. It was the negative particle, which were called electrons, and different elements had different numbers of electrons. The reason why he was able to say this with confidence, Thompson, is because he investigated cathodes made from different elements, and they all gave off the same types of particles. So he assumed that therefore every element has these. And he then constructed a new model for the atom, which was fundamentally different from Dalton's model. And that is that all atoms are made up of a sphere of positive charge, inside which there are tiny particles called electrons, which are the negative particles responsible for cathode rays, etc. Now, that became known popularly as the plum pudding model of the atom. So we were making advances in our understanding and once again notice of the nature of matter, but also of the nature of energy. And we then come, you see, we're now getting towards the end of the 19th century, and then we had a massive breakthrough once again. Who was Max Planck, who came up with his quantum theory. And when he came up with his quantum theory, which was our understanding that at a subatomic level, energy only can exist in fixed quantities or packets, what we call the quantization of energy. Now, I don't know how Max Planck arrived at this equation, which is the famous equation which we learn in schools, the energy of an electromagnetic wave. We now knew, thanks to James Clerk Maxwell, that an electromagnetic radiation is a waveform which can be well described, its effects were well known. The energy of a given wave is equal to Planck's constant times the frequency of the radiation. And the frequencies, the higher the frequency, then the greater the amount of energy. That was really the basics of it. How he got that, I really don't know. But I thought it might be just an interesting opportunity to tell you a little bit about Max Planck, who was really quite an extraordinary character. You see, when he was at school, he was brilliant at both music and physics and also at mathematics. And he really wanted, he could play the organ, the piano, the violoncello. He was a composer. He composed songs and he composed for other instruments as well. And his parents were desperately keen for him to become a musician, to study music. And the reason is because in music there was a great demand for composers, for musicians, etc. And it was a good way of earning a living. And physics was not such pure science was not such a thing. So Max's parents said to him, Maxie boy, you must try to study music. But Max Planck said, no, I'm far more interested in physics. And his parents said, but Maxie, they already discovered everything in physics. We've learned everything there is to know. We've done waves, electricity, the world is functioning. You don't need to do it. Max said, but you know what, I just like to learn a little bit better because I haven't really understood the physics very well, so I'd like to understand it just a little bit better. And understand it he did by gum, because not only did he understand it, but he came through with one of the greatest theories, the quantum theory. It was at this stage that the digital world was born. Because until that time, the macrocosm, the whole universe was, we can say, it was analog. Everything flowed, everything moved, analog mechanics, everything was infinitesimal stages, etc. But now, suddenly, a totally new dimension. At the subatomic level, dear friends, the world is actually different. It's quantized. You can have yes or no, 0 or 1, white or black. This was the great implication. It had great implications for the future, and of course, ultimately for the development of lasers, as I will shortly show. So once this theory had been put forward, once people started to understand the behavior of atoms at a subatomic level, in terms of electrons in this positive field, progress continued to be made. Now, I am just literally mentioning a small number, but there was a huge number of people involved. There was mathematics. It was really a massively fascinating topic on a great scale in a wide number of countries by a huge number of people. Now, Albert Einstein, of course, is famous for his theory of relativity, but he won his Nobel Prize not for relativity, but for the photoelectric effect. Now, what is the photoelectric effect? Well, essentially, it's light falling onto a certain material and causing it to emit an electric current. Now, if you don't mind, I'm going to just show you a very simple demonstration of the photoelectric effect. I have here a light meter. Now, this is a device which was used by photographers, and nowadays I suspect it's obsolete, but it was used until 40 or 50 years ago, and this was a very high quality light meter, the Western master, and I still use it when I do, and I'm sure people still use it, but it's wonderfully sensitive. And what I wanted to show you is at the back of it, this is what we call the photoelectric face there, or the cell, and on the front is a scale, which is essentially a voltmeter. Now, if I now take a torch, and I shine the torch, you see, and I shine it here, and I shine it on the back, then you'll notice immediately, as I shine it on the back, we have the demonstration of the photoelectric effect. Now, Einstein, I have to tell you, wasn't the first person to have observed it. This had been observed back in the 1860s, and Einstein was the one who conducted more experiments, and from this, he made another remarkable deduction. And he said that light can either behave as waves or as particles. Extraordinary. So we've now gone back. He said, look, you were right, and Highgate, you were right. That's an of course, they had viewed it differently. But we're now coming on to the duality of matter, the duality of energy, different ways of looking at things. Now, that's a very difficult idea to understand. How can something be a wave or a particle? How can it be just something? It depends on the way you measure it. That's the simplest way. It depends what type of experiments, what type of effects it produces. That's the way that you can prove these points, which are apparently a contradiction of terms. Now, Einstein had developed that. We then had another huge breakthrough, and that occurred in 1911. It was 1 year before Bohr, and in 1911, Ernest Rutherford brilliant New Zealand physicist, showed that atoms actually, the way in which the proton, the positive and the negative parts of an atom are arranged are quite different from what people had suspected hitherto. He destroyed, through his experiments with alpha particles and thin gold foil, he destroyed the model which had been put forward by Crookes of the, not by Crookes, but by Thompson, sorry, of the plum pudding model, and he proved that in fact atoms have a very similar structure to a solar system. And he said that in the middle of the atom there is a tiny, tiny, very dense nucleus made up of positive charge. This was Rutherford 1911. And around that, at a huge distance away, the electrons are found. So that was Rutherford's contribution, and very soon after that, in 1912, the Danish physicist Niels Bohr started to ask questions about the arrangement of these electrons flying around this nucleus, this very dense nucleus in the middle. And Bohr came up with he studied in specific the spectral lines of the element hydrogen. I've told you about these. And he was trying to work out where the dickens did these lines come from. We were getting closer and closer. This quantization of energy was beginning to get closer to people. They started looking for patterns in the wavelengths of these various spectral lines. And it was Rydberg who constructed an equation, and Bohr analyzed the equation, and he put numbers into it, and he did it with respect to one element only, and that was hydrogen. And the reason was very simple. Hydrogen had one electron, and they had several sets of spectral lines. And analysis of those spectral lines by a variety of physicists subsequently after Bohr showed that an electron can occupy only certain energy states with respect to the nucleus of an atom. So if you have a nucleus, then you have a quantum shell 1, quantum shell 2, quantum shell 3, and so forth. And depending on which quantum shell you had, then you had different numbers of electrons. And then everything started to fall into place. Mendeleev had constructed the periodic table of the elements in 1869 on the basis of chemical properties. The physicists constructed identically the same periodic table on the basis of the structure of the atom in terms of protons and electrons. And in a simple nutshell, the atomic number of the element told you what the element, the number of protons, and then as the number of protons increased, so the number of electrons increased, atoms were neutral overall, things started falling into place. And then, and this is where we can now start to understand, because we're coming on to the laser bit, because when electrons jump from one energy state to another, this is associated with a packet of energy which is quite unique, defined by Planck's equation here. And it's that packet of energy which manifests itself in the form of photons of a specific wavelength. And in a normal atom, in the ground state, the electrons occupy these ground states of the electrons. There it is, that's how they existed on. But certain conditions started to be understood, whereas if you irradiate them by heating or passing electric current, then they emit different the energy which comes off is directly related to the energy changes of the electrons within the atom. And that started to be investigated in greater detail. Now, in 1916, again Einstein, how he came across the idea of a stimulated emission of electrons. Essentially, stimulated emission, he had some sort of idea that perhaps you could get a very intense type of radiation, coherent radiation of one wavelength only, if you could somehow pump energy into an atom, get the electrons to rise into what they call a metastable state, and then as they drop down, they suddenly release all this energy which is coherent and in one wavelength in the form of an intensely powerful beam of light. It was Einstein who had that idea. How he had the idea, where he got it from, I really have no idea. But, and I can't possibly explain it, but I can tell you one thing. Einstein was Einstein. Szydlo is only Szydlo. So that is really the answer. The man was a genius, as we know. But the idea of a metastable state of electrons is something I would like to demonstrate. Certainly can't do it with electron, but what does metastable mean? It means something which is not particularly stable and which can very, very quickly change. And this is what he did with electron levels. Now, I have here, in this boiling tube, I have a small quantity of a supersaturated solution of sodium thiosulfate. Now, all supersaturated solutions are metastable. What that means is they very easily lose their stability and they change their state. You see, I'm just moving it around, absolutely nothing happens. But if I now drop in a crystal, a tiny crystal of sodium thiosulfate, a tiny crystal, there she goes, and now watch carefully, regardez attentivement, as we say in French. And very shortly, you will start to see crystals developing in our boiling tube. I'm going to get a little swirl around, and can you see the metastable state has been disturbed, and by gum, it hasn't lasted very long, that metastable liquid state. There you see masses of crystals coming down, and at the same time, it gets quite warm. Now, this, of course, is a demonstration of the phenomenon. This, of course, is used in hand warmers, as you know, etc. And the physics and the chemistry of that is a very interesting topic, but not for now. Now, once Einstein had actually had this idea of stimulated emission of electrons and photons coming in with exactly the right energy to produce, to multiply themselves and to produce more radiation of a coherent nature, no one really could see doing it experimentally. It was a theoretical idea. To cut the long story short, Rudolf Ladenburg actually demonstrated this in 1928, and by 1960, now you notice the gaps were quite long, Theodor Maimon actually built the first laser, and that sparked off an entirely new era in our world. As I've said before, one of the greatest discoveries of the 20th century, which today lasers are in every part of our everyday lives, as we know. So I just wanted to say, before I show you a laser which I have, I just wanted to show you that the laser was used for research purposes, and the brilliant English chemist George Porter was the first person who used a laser. This is 1967, just 7 years later. He used a ruby laser, and he used it to investigate photochemistry. Photochemistry is chemical reactions today in the atmosphere, a very, very important, a major topic today. All started off by Porter in 1967. He got a Nobel Prize with two other chemists, but he used a laser which he ordered himself to be constructed and was able to use. So I'm now going to finish off just by showing you once again, but this time the real thing, a laser. Now this is a gas. This is a gas laser, and we have our here. So here we have, this is a helium neon laser. It has a power supply here. It has a power supply here, and which is our battery pack there. Here you see is our optical resonator there. Our medium, our gain medium is the helium and the neon. The two mirrors, obviously we can't see everything there. And at the end here on my finger, I can show you the laser beam which is coming out. So that then concludes our demonstration, our short history of the laser. And I very much hope that having seen this little talk now, that you can understand a little bit about this, one of the most wonderful inventions of humankind.